So welcome to the CSP seminar this week. And it's our great pleasure to have Professor Rafael Frongillo from UC Boulder to give us a talk. So Rafael is an assistant professor in computer science at UC Boulder. And before that, he received his PhD from UC Berkeley in computer science as well. And he did a postdoc at Harvard and Microsoft Research, New York. And his research interest is mostly in theoretical machine learning and economics. And today he will introduce his work on design, loss function design based on new framework of new embedding framework. So let's welcome Rafael.
Thank you. All right, so yeah, thanks all for coming. This is kind of a mashup of a bunch of different papers on a similar topic, but the centerpiece is this new embedding framework that I'd like to tell you about for designing surrogate losses. So here are all my collaborators. Most of them are students. Jesse's now a postdoc at Harvard. And most of what I'll tell you about came out of her dissertation work. So yeah, to start off with, here, when you think about machine learning, there are lots of different paradigms. We'll focus mainly on supervised learning. So think just very generically about some prediction tasks. So maybe image labeling. So you have some complex feature vector like an image, and you want to assign some sort of prediction. And the goal is to find what I'll be calling a hypothesis or an algorithm, some model, which maps, in this case, images to a possible prediction. So, what kind of animal is in an image? And we want to find a good hypothesis. How do we measure that goodness? And that's kind of, loss functions is all about how to measure, well, I guess, badness. Right, and so the loss function we'll think of as taking a prediction and a label, and you want to measure how good or bad, in this case, that prediction was given that label. Okay, so hopefully that was, I added this slide because I thought my original introduction was too abstract, which I'm now going to transition to, which is, suppose you're given a generic learning problem in the form of a discrete loss. And I say discrete because for the talk, I'll assume that the problem that's given to you that you want to solve, you have a finite number of predictions and a finite set of labels. So things like classification problems, ranking, structured prediction problems, these are all cases where if there's a finite set of labels, you have a finite set of predictions that you want to make. And so, you want to find a hypothesis that is a good hypothesis. So one thing that you could, oh, sorry, and classification, by the way, if you want to see how this fits, typically the set of predictions, the set of labels are just plus or minus one for like, is this a positive or negative? This would be binary classification. And we use 0-1 loss, which says, look, if you were correct, then you have no loss. Otherwise, I give you a loss of 1. That's just one example. And so for all these other problems, you define it similarly in terms of some loss function. Okay, and if you want to find a good hypothesis, well, just take your data and find the hypothesis that fits that data best according to your loss function. That's sort of the natural thing that you would want to do. And this sort of direct ERM, where you're searching over the space of hypotheses that are taking predictions in R, which is a finite set, this is usually NP-hard. It's a finite kind of combinatorial optimization problem, and it's typically NP-hard. So what we do instead in practice is a surrogate. By the way, ERM stands for empirical risk minimization. So taking the empirical loss and minimizing that. So we usually do this surrogate version where instead you find a convex function, which now takes values in RD. So now your hypothesis will be mapping your features to some sort of vector, and think of it as like a score vector for the different classes or something like that. And then you can minimize this, but what are these predictions mean? Well, you need some sort of link function that takes these surrogate predictions and maps them back to the original space that you cared about, right? Because you really want to make predictions in this set script R. So you use a link function to take you back. So if you are familiar with support vector machines or logistic regression, or basically most or all supervised machine learning methods are doing something like this. And so the central question behind a lot of the work that this is contributing to is, when does this surrogate procedure work? Like, what surrogates can I use? I can't just pick any surrogate loss function here. Which ones are good ones? And what do I even mean by work? Well, typically the minimal thing that you would want is consistency, which says, so throughout the talk, capital L will be the surrogate, psi will be the link, and then little l is the discrete loss, which is like the problem that you're really trying to solve. We say that these three are consistent if whenever you have a sequence of these surrogate hypotheses that approaches the best possible surrogate loss, then when you link them, so this is like a sequence of hypotheses that are now mapping, through this surrogate, through the link back to R, right? So these are functions from X all the way to R. That sequence should approach the best possible target loss. And if you want to know how it's defined, like more formally, this convergence is in probability over the data being drawn from the true distribution. But kind of stepping back, what this is saying is, if you have enough data, then optimizing capital L and then linking is this, like, it should behave the same as if you were able to optimize the target directly. Question?
Can you remind me the relation of consistent to classification calibrated?
Yes. So calibration we'll get into later in the talk, but calibration is one way of achieving consistency. Well, in fact, it's equivalent. So yeah, this is really the thing that you want, and calibration allows you to prove this. It's a good time to ask other questions if there are any. Yeah, go ahead.
So a typical link function is like an argmax.
Yeah, so in classification, right, you could take the highest score, and that's the label that you're predicting, or we'll see some other exotic links functions later in the talk too. Yeah, I think the classic one is like the sign function for logistic regression, something like that. Yeah, we'll see some examples in a sec. Yeah.
What should we think the script H and script H prime, the sets of, I guess, hypothesis calculators or whatever, what kind of sets are we thinking?
Yeah, so those are like, think of those as linear classifiers, or I'll abstract it away for the whole of the talk as much as I can get away with.
Okay.
But yeah, that's the kind of thing. Is what space of models are you working in? Yeah.
What is I next year with respect to H?
Yeah, so I'm suppressing a lot of the details, but think of this as, hypothesis I is the one that you get after collecting I data points and then minimizing according to this. And we're taking the limit as I get more and more data. Yeah.
Can you help me get my mind around that term hypothesis? I think of the function, right? Not a value, right? So it's
right.
Given data, I guess it makes hypotheses, right? So you're just calling it a hypothesis.
Yeah, I don't know. I haven't thought much about it. I just, for some reason, that's the word that people use. Yeah. Yeah, but model, you can think model as well. Yeah. Okay, so here's kind of the design question. If I gave you some new prediction task, how would you design a convex surrogate that was consistent? And it's really not obvious. And in some sense, the state of the literature kind of reflects that designing surrogates has been fairly ad hoc, that there's some new task and people think about it for a while. They try to borrow ideas from other areas and, you know, okay, this looks kind of like classification. Maybe we can use some ideas from there. But the result of that process has been a long list of surrogates that were proposed at one point. They seemed like great ideas and were later shown to be inconsistent. And we'll go through examples of each of these and some more in this talk. So I think, you know, we're still in a place, I would say, even after this framework that I'll tell you about, but hopefully we got closer, where we don't know a whole lot about consistent surrogate design, and we would like to get more systematic ways of doing this. But what I'll tell you about is a new embedding framework to design surrogates and construct, so we can construct surrogates and prove that they're consistent. And we can understand using the same tools, essentially, to understand existing surrogates of a particular type. So here's what I'll tell you about. So I'll kind of, oh, sorry, yeah.
Yeah, so I just had a quick question about the surrogates being shown to be inconsistent. So is that because they were designed before there was a framework to show consistency, or like new results came out that showed they were inconsistent? Or did they just miss like counterexamples when they originally proposed them?
I would say both. Yeah, so in some cases, we didn't really have a framework to even define consistency, and it just seemed like good ideas. But I would wager that somewhere in a room, somewhere in some university, there are people sitting around a table proposing an inconsistent surrogate right now. You know what I mean? So like, yeah, it's a mix of the two. Yeah.
Just a quick question. Why do you use the word like embedding framework? What do you want to try to?
Oh, we'll see. Yeah.
Can I look at the definition of consistent again?
Sure.
So, so we need both a good design of a lowercase l and the link function in order to be consistent.
Yeah, so you're given this target problem, this discrete problem, and you would like to design these two, where L is consistent and convex. Yeah. Okay. So yeah, so I'll tell you sort of the highlights of the embedding framework. And I had to choose just one of the details to take you through a proof sketch. So I chose the link function construction because I think there's a lot of interesting pieces going on there. And then I think what really brings it alive is going through a bunch of applications. And then I'll tell you about some future work that I think, like I mentioned in the beginning, I think there's a lot that we still need to do to understand this space better. Okay, so just to get a little more concrete in the mathematics, so we'll be reasoning about these four spaces. So you have a finite set of possible labels, and we'll be thinking about distributions over these labels, which all periodically depict this way. So this is like this is a probability simplex on 3 outcomes. So this is a distribution that's, say, close to uniform, which would be about here. And this is the point distribution on label 1, point distribution on label 2, etc. If you've never visualized it that way, we'll see a bunch of these diagrams. You have some discrete set of predictions, and your discrete loss, again, is taking, you know, given this prediction in this label, what is the loss? And the surrogate is defined similarly, but the predictions are in RD. And one concept that will come up constantly in the talk is this idea of a polyhedral surrogate, which is just a piecewise linear and convex surrogate, which in the literature you may see phrases like hinge-like surrogates referring to hinge loss, which we'll also see a bunch.
So for each y value, it is piecewise linear and convex.
Yes, thank you.
Okay.
Yeah, for each fixed label, you get a
Right.
polyhedral function. Yeah. Okay, and another concept that comes up a bunch is optimal sets. So this is a function we'll use this as a function from the true label distribution to the optimizers of the loss. So for example, for the discrete loss, looking at the expected loss when the label is drawn from P, what are the reports in R that minimize the loss? So, you know, generically, this will be a single report. So a singleton set, but there might be ties on the boundary. And, you know, for example, in classification, if P is 50%, then the minimizer of the loss will be both plus and minus. And similarly, we can define this for a surrogate, and there, because we'll be thinking about convex surrogates, we'll get nice convex sets for our optimal set. So these are the reports, as I'll call them, the reports that optimize the loss exactly when the label is drawn from that distribution P. So as an example and a visualization for 0-1 loss for 3 classes, this is what the opt set looks like. So here, the optimal set is just the singleton 1. Here it's 2. Here it's 3. On this boundary, it's the set 1 and 3, and here it's 1, 2, 3. So this is just the mode, the most likely label. So classification is asking, what is the most likely label? It's another way of thinking about classification. Questions on these? I know this might be a different way of looking at things that you've already seen.
How is the report related to the link function?
Yeah, so the link essentially is trying to take points that are optimal here and make sure that they link to something optimal here. That'll be a major theme. Yeah, if something optimizes the surrogate, it turns out you need to map that to something that optimizes the target. So was one. Turns out you need more than that, but it's essentially it. Okay, so and then just to recap on this, so this cell here is the set of distributions where the most likely outcome is 1, right? So that's how to visualize the mode. All right, so goodness. So our goal again is to design a consistent convex surrogate given discrete loss, and here's some idea, which a bunch of people have kind of referred loosely to as an embedding. So it's this kind of ill-defined procedure for now, where you take your discrete reports, you map them into RD in some way. So you kind of embed them using this function phi. And on these points, you match up the surrogate and the target loss. So you make sure that the loss values match. And then the mysterious step is you somehow convexify this in a way that makes it all work. But you know, it's kind of an intuitive thing. You take your target, you find a way to embed it, and as long as you get something, you can do it in a way where you get a convex loss, you kind of convexify everything. And hopefully this works okay as a way to design surrogates. So you can think of the hinge loss in this way. So this is the hinge loss. It's the, max of 1 minus yu. So y is either plus or minus 1, and u is any real number. So you get, so this is when the outcome is 1, this is the loss. So right, if you predicted 1, then you get loss of 0. If you predicted minus 1, you get a loss of, well, in this case, 2. So it's not quite 0, 1, but it's twice 0, 1. But you can check that the loss values match 0, 1, and it's convexified. So at this point, that's an embedding, but I'll be more formal about it. So the question is like, okay, we know the hinge function that's used in support vector machines, we know that that's consistent. So maybe there's something to this. All right, so here's the formal definition as we give it. So first we need this concept of a representative set. I think it's a somewhat intuitive concept. So a set of reports is representative if at least one of these reports is always present among the optimizers of the loss. So no matter the label distribution, there's something in U that optimizes the loss. And with that, an embedding is simply what I already told you. So it's a map from these discrete reports into RD, where the loss values match. So for every R and Y, the surrogate at the embedded version of R and Y is exactly the same loss value. And the only other condition is that if I take the surrogate, if I take the target reports, the discrete reports, and map them into RD, I get a representative set. Meaning at least one of them is always optimal. Well, the quantifiers was not quite right. Always, at least one of them is optimal. So let's just to exercise this definition, let's just verify that Hinge embeds twice 0-1 loss. So we already checked that the this first condition, the loss values match. So we just need to show that we get a representative set. And again, representative means it's always present among the optimal set. So here the map is just the identity. So I take -1 and I map it to -1. I take +1, I map it to +1. And I've worked out for you the optimal sets for hinge loss on the right here. So for example, if the probability of outcome 1 is 1, then you get exactly this line here. So the optimal set is 1 all the way to infinity and so on. So that's where I'm getting these. And you can just check, okay, there's always either 1 or -1 or both in these sets. So it's representative. Make sense?
Is the logistic loss consistent and representative?
The logistic loss is consistent. It's not an example of an embedding.
Okay.
In particular, you would need the whole real line to get representativeness, because for every distribution, you get a unique and different optimal point. Yeah. And logistic is not a polyhedral loss, and we'll kind of see why that's related to embeddings. Yeah. Okay, so let me tell you kind of the main results. The first is that, and I guess it might seem surprising, it certainly was to us, that if you have a surrogate that embeds a discrete loss, then it's consistent for some link. So, you know, this definition, it seemed kind of weak, or at least it still does to me. There's something is really happening here about the representativeness that's really driving this. So if a surrogate embeds a discrete loss, then it's consistent for some link. And for any discrete loss, we can come up with a polyhedral surrogate in particular that embeds it. So once you combine that with the first result, for every discrete loss, we have a way to design a convex consistent surrogate. Now, it's not like we've solved everything, because there are reasons why you might want some surrogates over others. So this is just one surrogate, but you know, it's convex and consistent. And the third one, which we'll talk about a bunch in examples. So as I mentioned, we have a long history of inconsistent surrogates. Well, it turns out if they're polyhedral, then you can ask this following question: what is it solving? Because it must embed something. It turns out, you know, every polyhedral surrogate is embedding some discrete loss. So if you have an inconsistent surrogate, you can ask, well, it's not solving what you wanted it to, but what is it solving? And it turns out you get interesting answers. All of these results I've stated as existence, but we give construction. So we give a construction to sort of invert the embedding to get a link, and I'll tell you a bit about that. I don't have time to tell you about how to construct these polyhedral surrogates. That's also pretty cool. We use a construction based on convex conjugate duality. And for this last one, there's this key lemma that we'll use a couple of times in the examples, which is if I have a finite set of points that are representative for the surrogate, then the surrogate embeds itself restricted to that set, meaning if I only allowed you to report something in that representative set, now it's a discrete loss, and that's what embeds. It's actually not even a lemma the way I've defined everything. It's sort of a trivial statement, but maybe not obvious in beforehand. Yeah, so if you are given a polyhedral surrogate, the main game is find a finite representative set, and then you'll sort of understand what that surrogate's doing. All right, questions before we dive into the link? Yeah.
Are there any limits to like, or any restrictions on like how you construct this piecewise linear and convex function? Because it seems like you could define some function that has like an unlimited number of, or like an infinite number of piecewise.
Yeah, so thanks. Yeah, I swept that detail under the rug, but polyhedral implies a finite number of pieces. Yeah.
So can I ask a question, Raf? I'm online.
Oh, yes, please.
So to follow up on the previous question, actually. So like sometimes your loss might be discrete, might be defined over a very large scale space. Like for rankings, you would have, you know, m factorial rankings of m objects. Does the finite number of pieces, do they kind of sometimes blow up with relevant parameters, or do you always get some kind of a compact polyhedral set?
Yeah, great question. I assume probably they would blow up. We did not really look into that. I think there are lots of interesting questions about how the geometry of, in particular, this surrogate that we show how to construct. Yeah, we don't really understand necessarily combinatorial properties of it or anything like that. Yeah, I think that's really interesting.
I have a quick question.
Yeah.
So for these like polyhedral surrogates, is it like a one-to-one correspondence with losses, or will you have like multiple equivalent like polyhedral losses for one surrogate loss? Or like I'm just wondering, like, can you have equivalent losses, or is it a unique mapping?
It's definitely not a unique mapping. So you can add like I could take Hinge Loss and just bend the parts outside of the interval -1, 1, and it'll still behave exactly the same. So there are sort of trivial things you can do like that. But maybe if you like modulo those kind of tricks, it might be unique-ish, you know, if you, yeah, that's a good point. Yeah.
I'm using notation like L conditional use.
Yeah, I haven't really defined it. It just means if I restrict the loss, yeah, what I really mean is like if I restrict this function to u cross y. You see what I mean? Like I think about it as a discrete loss where this is u and I match the values. So I'm taking the function restriction of this to u cross y. I'm only allowing you to report something in u. Okay, so I'll tell you a little bit about this link construction, and then we'll go through some examples. Oh, yes, and so I alluded to this earlier. So you see that there's this tight correspondence between embeddings and polyhedral surrogates. So every discrete loss has a polyhedral surrogate that embeds it, and every polyhedral surrogate embeds a discrete loss. The issue here is because there are other surrogates that embed things. So I could similarly take Hinge Loss and then curve up the part outside of the -1, 1 interval, and it would no longer be polyhedral, but it would still embed 0, 1 loss. So, but for the most part, I think it's a good heuristic to say embeddings are roughly equivalent to polyhedral losses. All right. So let me tell you a bit about calibration as the question that started us off, and consistency. So basically consistency as it's given to us as like this is not a very easy definition to work with. You have to seemingly reason about all sequences of hypotheses that are approaching this best loss. And it turns out there's this nice definition called calibration, which I'm sweeping some assumptions under the rug, like assuming that the best possible hypothesis is in your class. But I'll just kind of abstract away those details for this talk. We say that a link is calibrated if, so I'll just kind of zoom through this. So the minimum possible loss that you could achieve, this is expected surrogate loss, while linking to something that's not optimal under the target. So I'm saying, like, among all reports that will lead you astray, so link to something that's not optimal, what's the best possible loss that you can get? That has to be strictly greater than the best possible loss overall, and in particular among reports that do link to the optimal target. So it's like saying, yeah.
Don't we usually talk about calibration of losses and links together with respect to a loss? Or...
Yes. Yeah, so usually I would write it in the same way. I was just lazy.
Right. Oh,
yeah.
Okay, I see.
Yeah, so surrogate comma link pair is calibrated for the target. Yeah, thanks. So at a high level, what we're saying is that you can't approach the optimal surrogate loss while linking to something that's not optimizing the target. And you can see why that would be bad, because your learning algorithm or your hypothesis could be doing something wrong the entire time while getting better and better loss. And it turns out, what an important piece of this though is that I have no X, I have no features. I'm not thinking about hypotheses. I'm just thinking about surrogate reports. And that's much, much easier to work with. So it turns out this is an equivalent to consistency under some assumptions. And this is a short distance from a similar notion that we use. So when L is a polyhedral loss, it turns out that you can even reduce this further to something called separation, where basically it's a similar condition, but if your report U is linking to something that's not optimal, then it must be at least epsilon far from the points that are optimal. Sorry, for the surrogate. So here are all the points that are optimizing the surrogate. If you have something that's linking to a suboptimal target, then it must be far from the optimal surrogate report set. So yeah, this idea of separation is key to our construction. So we basically, we have this embedding, and we want to somehow separate, we want to divide up the space so that we have a link that's kind of has a buffer around each of the points. And what we do know is that each of these points, when you link them, should go right back to where they started from. It's not necessarily obvious, but because we match loss values, this point will be optimal for the surrogate if this point is optimal for the target, because they have the same loss values. So we know that the link must be inverting these arrows, but it's not clear what to do in the rest of the space. And the idea is essentially, and I'll just kind of go a little fast through this, but I'll give you the taste of it. The idea is to construct some link envelope. So you pick the epsilon and some distance, and you enumerate all the possible optimal sets for the surrogate. Oh, sorry. So you initialize the link envelope to be everything. So what we're going to do is we're going to impose constraints on the link function so that it's enforcing this separation. So I go through all these optimal sets for the surrogate, and I thicken them by epsilon. So here's, this triangle is an optimal set. And here's the thickened version. And for each of these, I'm going to require that the link function link to something in RU, where those are the points that embed into U. So if these are the embedding points, everything in this wide region must link to either 1, 4, or bot. Similarly, in this square, everything in here must link to 2. That's the point that's embedded in there. And I keep going, placing all these restrictions. And if at the end, I have a candidate to link every point, so the link is nowhere empty, then I just take anything in there. And you can see that for larger values of epsilon, so here's a particular value of epsilon, if I extended this, if I raised epsilon anymore, then I would have an empty region in here, because it would be saying, you have to link this point to 2, but this region would say you have to link this point to 1 or bot. So we get the empty set. So, but if that doesn't happen, then that's how we define the link.
Sorry, what is the perpendicular shape?
This one,
Yeah.
bot. It's just a, we'll see. It's just \bot in LaTeX. I don't know what you actually call that symbol.
But what is it representing?
These are just possible reports. This is coming from an example where it's multi-class classification with an abstention option. So that would be an abstain report. Yeah.
Sorry, Raf, I don't know if you already answered this. How is K chosen? The dimension in which you embed.
Oh, sorry, this should be D. This is the same D.
Oh, it's the same as your D earlier. Okay.
Yeah, sorry. This is,
And
yeah, D is just, yeah, that's a good question.
yeah, then how is D chosen, I guess?
Yeah, so D is just, for now, let's say we're given a surrogate that's defined in RD, and we want to construct a link. So yeah, D is kind of given to you at this point.
But should we be thinking of it as on the order of the cardinality of your reports, you know, so you kind of splay the points out along different axes in a higher dimension, or is it typically less than that cardinality?
Yeah, great. So this is an example where the cardinality would be log the number of, or sorry, the D would be log of the number of labels. Yeah, which is what's cool about this example. Yeah, so the theorem that this works basically breaks into 2 pieces. One is that for sufficiently small epsilon, you do actually get non-empty everywhere. So there is some choice. And that given that choice, you get consistency. And the hard part is the first part. So you have to show that if these U sets intersect, then the corresponding RU sets do, which means that there is a valid choice in there, because if they didn't intersect, you get the empty set. And that has to remain true even by thickening by epsilon. And like I said, you can take epsilon too large, like to get this point to be the empty set, because the constraints, you know, leave you with nothing. But it turns out for epsilon small enough, you can always do this. And then sort of by definition, whatever you get will be separated. So we'll, you know, that's what gives you consistency. So yeah, I know that was kind of fast and didn't really tell you much, but hopefully it gives you a sense of like how we're able to sort of construct things even in this generality. And the implication here is that for every polyhedral loss, we can define a consistent link. And so since we already know for every discrete loss, you get a polyhedral surrogate that embeds it, this means for every discrete loss, you have a consistent convex surrogate. All right, yeah, any questions on that real quick before we see some examples?
So crucially here, you need discreteness because otherwise you won't be able to epsilon separate things. And
Yeah, that's good intuition, I think. Certainly if you have a continuum of reports, you wouldn't hope to have separation.
right.
So yeah, yeah, I think there are some ideas here that can extend, but not many. It does seem pretty specific to the discrete case.
Is there also a trade-off between the dimension D and the complexity of the polyhedral function that you will construct for the discrete loss? Is it like, oh, if I can have as many dimensions as my reports, then maybe I can just put one location?
Yeah, I think that relates to Ambuj's question. That,
Right.
yeah, I don't know. I probably would have similar intuition that the more you try to cram it in smaller dimensions, it's
Weirder
gotta get,
dimensions.
yeah. But
Right.
yeah, we don't have much in that realm. Okay, and the last thing I'll mention is that if you know about surrogate regret bounds, we can show that for any polyhedral loss, you get a linear conversion from the surrogate rates. So this is getting at, you know, the consistency definition was saying something about approaching or convergence and probability. So this is about the rate of convergence. And there's a rate of convergence for the surrogate. There's also a rate of convergence for the target. And what this is saying is whatever the rate of convergence is for the surrogate, it'll be the same for the target. Whereas for other surrogates that are not polyhedral, you often get a slower rate for the target. So the surrogate's converging faster than the target is. So that's kind of nice.
So by linear conversion would be just like a scale factor, basically.
Yeah,
Yeah. Okay,
yeah.
constant.
yeah, and that's what we show. It's just some constant that comes out. Might not be a great constant.
Yeah, okay.
I'm a theorist. I don't know. I haven't thought about it. Okay. So yeah, let me tell you about some applications, which I think kind of helps this come alive a bit. So to recap, you know, there are these sort of three key results: constructing a link, constructing a surrogate, and then this kind of inverse problem of given some surrogate, can I say something about what it's doing? And for that third one, like I said, the key step is finding this finite representative set. And if you can do that, then you know that the surrogate will embed itself restricted to that set. And you can ask, okay, this is now a discrete loss. Is that the one that you were hoping for? If so, great, it's consistent. If not, it's probably not consistent with what you wanted, but you can still ask, okay, what is it consistent for? Okay, so I'm not sure I'll have time to get through all of these, but we can try. Okay, so first up, this abstain variant. So here you have, it's like a classification problem, but you're allowed to abstain. And if you abstain, you get a constant loss of 1/2. Otherwise, you get 0, 1 loss. So 0 if you were correct, 1 otherwise. And if you think about it, visualizing a probability simplex, you get optimal reports that look like this, which say, if you're at least 50% confident in any outcome or any label, predict that, otherwise you should abstain. And yeah, so Ambuj and the co-authors have this very nice BEP surrogate, binary encoded predictions, that somehow managed to cram into log n dimensions if there are n labels. So very cool surrogate that's consistent for this problem. So that was actually a motivating example for our whole framework. And sure enough, it is an example of an embedding. B here is just like a way to encode the label into a binary -1, 1 vector. And the embedding is exactly those encodings. And you map the abstain to 0. So this is only 3, whereas this is depicted with 4, but like 1 would go here, 2 would go here, 3 would go here, something like that. And then the abstain would go into the origin. So it's an example of embedding. And I think what's interesting here is that if you use this construction for the link using the infinity norm, then you actually recover the same link that they originally proposed. And you also recover the surrogate regret bound. So that was like a nice validation of the framework that maybe, you know, it could have saved some work there. And I think it's also interesting to just throw in the construction with a different norm, and you get a different link function, which is also perfectly consistent.
This is the norm for computing the distance.
Yeah, this is like the separation in the surrogate report space. So how how do we measure distance there, right? And as you can see, you get very different shapes. So this is the L infinity ball around this point, whereas the L1 ball, you know, it's much more snug up against the boundaries of the others.
And so then the rates for these two different norms are
Yeah, so that's you get a different constant.
different.
I actually think that the one norm is worse, and I think their original link was the optimal rate. And I don't really understand why, but I think we worked that out at one point. Yeah. Yeah, so here's another example, which I think this is one of the most interesting examples, at least historically, is top K classification. So here you get to predict a set of labels of size K, and it's basically 0-1 loss generalized to that. So 0 loss if the outcome is, or the label is in that set. So think of like a search problem. You show a bunch of search results. Did they click on one of those or not? And so there are all these surrogates that have been proposed. The details don't really matter, but you know, I'll show you anyway. Look, you know, here's some surrogates. And Yang and Coello showed recently that they're all inconsistent. Yeah, and these are all polyhedral, and they concluded that with, and this is a quote from their paper, with hinge losses, which I interpret to mean like polyhedral hinge-like losses, convexity seems antithetical to top K calibration. Like, seems like maybe you can't do these both. But wait, we just showed that every discrete loss has a polyhedral surrogate. So easy enough. You can just throw in the construction and here's what you get. This was a bit of massaging from the original form, but this is like a slightly simpler form for it. But yeah, in our paper, we kind of hypothesize like what it all means, but I think it's almost even a better underscore of how useful the framework is, in that it's not clear what's going on with this surrogate, but you know, so maybe you wouldn't have come up with it. So maybe the framework's useful for you know, coming up with a surrogate like this. I think what's also interesting about this particular example is usually in top K classification, you use an argmax link. So you kind of score each of the possible labels, and then you take the top K of those. And you would hope that that same link would work for this, but our construction does not at all guarantee that, right? It just says there's some link and it shows how to construct one. But you can use that construction to verify that indeed the argmax link that you would hope for is contained in the link envelope. So that means that it is a consistent link, even for this new weird surrogate. Yeah.
Did you test this?
Yeah, so that was something that we proved in the paper.
No, I mean, like, did you?
Oh, did we run it?
Yeah.
Yeah, we did actually, which is not typical for me, to actually like
Apologize, it's okay.
to do something with real data, but I didn't do it. My students were helping me out with that. And yeah, it doesn't blow the others out of the water in the way that we would have hoped. But there are definitely data distributions where the consistent one beats the inconsistent ones, which I would have thought would have been easier to show empirically. Yeah, and it could be related to some of the combinatorial optimization properties and things, why the other ones did pretty well in practice. Okay, and then finally, we have all these inconsistent surrogates. So you could ask, you know, using the third part of our framework, like given an inconsistent surrogate, you can still ask, what is it doing? And it turns out they're all kind of interesting variations on the top K problem, often where you're allowed to predict a set of smaller size than K. So here's what L4 embeds. It's like 0-1 loss, but you get a lower penalty if you have a lower cardinality of T. So if you put all your eggs in a smaller basket, then your penalty for being wrong is smaller. So it kind of rewards you. If you're confident in a smaller set, it rewards you. So, you know, some of these might be actually interesting to use in some applications. Okay, I wanted to plug this application. So back in the day, we were trying to find surrogates for multi-class classification, and Weston and Watkins proposed some hinge-like surrogate. It was later shown to be inconsistent by Ambush and Peter Bartlett. And Clay Scott and Yutong Wang showed what problem it does solve using our framework. And it turns out it's some variation of 0-1 loss where you, again, you similarly can incorporate confidence. And for time, maybe I'll skip the details, but yeah, check out their paper. It's super interesting. Yeah, and let me skip this. So the final example I wanted to get to because I think it illustrates a different facet of this framework. So I'll quickly tell you this motivation for this problem. So in structured prediction, we think of settings where you have lots of different related subproblems, and you would like to think of them as a holistic single prediction. So for example, part of speech tagging in a sentence, you could think of it as taking each word in a sentence and tagging the part of speech, but you're really doing that for an entire sentence at once. And you would like to evaluate the loss on the entire sentence. And similarly, I'll use this example going forward, image segmentation, you try to segment an image foreground and background. And it's really a pixel by pixel prediction, but you'd like to evaluate it on the whole image simultaneously. So one way to do this is to pick a submodular function and look at the set of pixels that you got wrong and define the loss to be that submodular function applied to that set of pixels you got wrong. The idea being that the more errors you make, the diminishing additional loss that you get. So you look at the set of pixels you got wrong and you kind of holistically evaluate that in a sensible way. And there's this interesting surrogate based on the Lovaas extension that's polyhedral that was proposed for this problem. But unfortunately, it's not consistent. And it turns out the BEP surrogate that we already saw is a special case of this surrogate, which is one way that you can see it's not consistent. Okay, so you can ask, what does this thing embed? For which submodular functions is this consistent for the original problem? Like here's one where it's not, but maybe there are others where it is consistent. And it turns out that the problem that it does embed is interesting in its own right. So constructing a link for it is interesting. So let me see. Yeah, so it turns out that a representative set for this loss is -1, 0, 1 to the k, meaning instead of picking just -1 or 1 for each pixel, you can also pick 0. And semantically, picking 0 acts like abstaining on that pixel. And because of this, there's a lot more work once you get this, but you can show that it's basically only consistent in the trivial case. I mean, I haven't gone into submodular functions, but this is basically the trivial case where you would never do any of this anyway. So it's basically always inconsistent, but it does do something interesting. It's allowing you to abstain on a pixel by pixel basis. So a lot of work later, and I'll skip the details, but there's a lot of crazy geometry trying to apply the link construction in this setting. Like it got real gnarly, and here's the link. It's not like a simple function. You have to like first sort things and take gaps and all these things. But we really needed our construction here because simple threshold links, like you might say, okay, if you're close to 0, threshold that to 0, otherwise take the sign. It turns out that's not consistent for this problem. And so here's another rare deviation of a theorist doing things with real data. Here's what this link does in practice. So here this blue region as the abstained pixels for this foreground background. So it seems to work pretty well in practice, actually. So yeah. All right. So let me wrap up because we're almost at 5 o'clock. So I've shown you this new framework that has a way to construct links and surrogates, but also take an existing surrogate and kind of figure out what it's doing. And as we've seen, you know, this kind of goes back and forth. People are coming up with surrogates, and if they're not consistent, maybe they're doing something else that's useful. I think, you know, first open direction is just apply the framework. Lots of structure prediction problems. The second, I think, direction that's interesting is really about that D. So how low can we make that D in this construction? And, you know, this BEP surrogate is super cool in that it gets all the way to log n if you had n. And that's great for structure prediction because typically the number of label configurations is exponentially large. And that's the same for this this last example that we saw. The number of, you know, think about the number of pixels, and then 2 to that is the number of possible label. That's the number of possible segmentations. Like, you don't want something linear in that space. So yeah, so how low can we go? When can we get log n? I think, like, more broadly, there's some very interesting questions about strongly convex surrogates versus polyhedral surrogates. So I've been talking mostly about polyhedral, and there's some benefits there. Strongly convex surrogates typically give you fast convergence rates. But, you know, probably once you translate it to target rates, because as I mentioned, the fast rates slow down when you translate them to the target. So they're probably pretty similar once you look at the target rates. But there are reasons to think that polyhedral losses might be more statistically efficient in some sense. So I think that's a really interesting question to explore. And then finally, I think there's more that we can do to understand consistency itself. All right, and I'll stop there and take questions. Thanks.
Ross, this is Clay.
Sorry?
This is Clay. Can you hear me?
Yeah, I can hear you.
Question, I'm curious, especially since Ambuj is here, about the abstention example. If the loss for abstaining is not 1/2, but some other value, does it drastically change the embedding dimension?
Yeah, right. So I always get this backwards, but if this, let's see, I think if it's smaller than 1/2, then the dimension jumps all the way up to n. If it's greater than 1/2, wait, did I get that right? No, if it's greater than 1/2, then it jumps all the way up to n. If it's smaller than 1/2 or equal to 1/2, then it's log n. I think that's the answer. So yes, it does have a big impact. And one way you can see it is it's about the geometry of the boundaries here. So if the penalty for abstaining is lower, then sort of the underlying geometry looks the same. The abstain region gets larger. The number of distributions where you'd like to abstain gets larger.
Yeah.
But if it's smaller, then you pick up extra boundaries between the cells that make it, you need n dimension. Yeah.
Right. Yeah, that would get really complicated with many classes.
Right. Yeah, great question though. Yeah.
So this, you said you have like a framework. This is like some sort of like algorithm. Is it like just a set of like theorems that you follow, or like?
Yeah, just pretty much a set of theorems that I told you about. Yeah. So framework in the sense that it's a definition that, you know, it seemed kind of weird at the beginning, you know, but it turns out to be a very useful way to think about these. Yeah.
Right. Is this something that like could be sort of automated to a certain degree, or is this something that has to be like derived manually?
Yeah, I think we got this question in the review process also. I think I think of it as mostly as something that's done at the symbolic level. Because usually the discrete losses that you're reasoning about, they have some kind of parametric form that, like multi-class classification. It's not like you sit down and think about what to do when you only have 4 classes and then start from scratch with 5. You really want something that lets that be a parameter. So for that reason, I think a lot of these problems you would want to proceed at the symbolic level so that you're not just taking some specific loss. It's usually like a family of some kind. Yeah, so for that reason, I think about it as some mathematical tools, but some of the constructions you can proceed, and we have tried to do that. And then small discrete losses, you can do it, but probably the runtime of any of these theorems when you translate it is not that great. Yeah.
Are there like specific cases where it's really hard to use this?
Yeah, I don't know. I would say in this example that I showed here, where is it? Yeah, this was pretty hard. That definitely, it actually started out as an example in the original paper, and then it just grew into its own thing because it was just so gnarly. And I didn't have time to mention this, but part of the reason it was so gnarly is that if you try to apply the construction directly, you get a link envelope that depends on the particular submodular function that you chose, but you don't really want to do it for every single submodular function. Like, how would you do that? So we had to find a way to construct a link that would simultaneously work no matter what the function was. So that's the kind of thing I mean, like, it's more a symbolic tool in a lot of these settings. Yeah, but it's a good question. I don't know if we know when it's hard. Yeah.
When you said the dimension jumps to n under the construction, that's saying that the construction doesn't work. Do we also have a lower bound on the
Oh,
dimension?
yeah, so that was
That
n was,
actually at least n.
yeah, the n was a lower bound. We don't have a log n lower bound. We have an upper bound because we have a
Because you've done
certain,
that.
but yeah, you can show a lower bound of n,
I see.
as it turns out. Yeah. Yeah, and there's some papers that look into lower bounds, and that's a really hard space, but also very cool because you can start to separate things and say, okay, this is a problem that has to have a large dimension.
Right.
Yeah, and there are a lot of really fascinating open problems there. We know a couple things, but yeah.
So I'm just wondering, like, is there a way conceptually, like, trade the dimension you're working in for some like degree of like calibration? Like, could you make it, is it like a binary, like yes it's calibrated, no it's calibrated, or can you like slightly make it less calibrated but reduce the dimension that you're working in?
Yeah, I think there are definitely some concessions you can make to make it less calibrated. This is a all or nothing, what we've been talking about. So one way you could do it is, I skipped past this figure, but this is for Weston Watkins. These are kind of the sets of distributions where you have non-calibration. And one explanation for why Weston Watkins works well in practice and sometimes is that maybe your data just isn't hanging out here. And these would be like images where you have a near tie between cat and dog, something like that. And like maybe you don't have a lot of images that look like that, and then it should work fine. So yeah, I think this is a nice way to quantify like concessions and consistency. I think there are others too. Yeah. But we know even less about how that trades off with dimension.
Is this like, could this conceptually be moved to something that's not piecewise linear? Like, could you move this to like continuous functions at some point, or is there like a conceptual reason you couldn't do that?
Yeah, a lot of these results seem specific to polyhedral losses. We have some extensions, but yeah, the smooth case seems very different, and it kind of gets at something I was mentioning at the end, which is smooth losses seem to, in some sense, require you to learn all the conditional class probabilities, like implicitly. Although if you have a lower dimensional surrogate, that might not be true. And yeah, I would say probably new tools are needed. Yeah.
What about a smooth convex loss that could approximate your polyhedral loss in a way that you get new representative points which are close to the initial ones and still minimize the smooth one, something like that?
Well, if you have a smooth loss that's sort of smooth in interesting parts of the surrogate space,
Right.
you probably need an infinite representative set. Because as you change the distribution, the point that's optimal will slightly move in some interval.
Oh, okay, right.
So that's why it's just a
that's the problem.
fundamentally different set of
Right,
tools.
right.
Yeah.
Sorry, yeah, that makes sense.
A question that is less about this. Is this anyhow like kind of relevant to the proper scoring rule? Any aspect? So it's like you at the beginning you have a loss function that is not convex, probably improper, kind of can map it to a convex function, but it's kind of proper. Is that intuition?
Yeah, so you could think of, let me see if I can jump to it. Yeah, you could think of this loss as defining what proper means in a sense. So if you wanted to learn the conditional class probabilities, then the set of reports would be a probability distribution. And then the label, you'd use a proper scoring rule. But here, like we're basically saying, well, I don't necessarily want to know the conditional class probabilities. I just want to know which label is most likely. So you can think about it in terms of proper scoring rules, but it's like it's eliciting a different property. All right, I think probably we should wrap up. I mean, I'm happy to chat, but I don't know what you're.
So maybe you can stop here. Individual questions you can chat with Rafael.
Yeah, I can hang out for a couple minutes. Thanks all for your attention. Thanks, Zoom folks.
Thanks, Raf. That was super cool. Thanks.
All right.
Great talk.
Oh,
So to know
Yeah.
wherever.
I'm just walking to my car, so I'm good
Okay,
to go.
okay,
Yeah.
okay. Yeah, so
Thanks a lot.
Thank you. Thanks for talking.
Oh, I think I have your adapter.
Thanks for the.
Or maybe I don't want to break it. Someone has back strength training soon.
Oh.